Hello world, welcome to my channel. I'm Bound to Be Coding, and this channel is all about a single-player 2D survival game, hobby project of mine, that I'm working on called A Struggle to Survive. It is set in 1820 America during the time of the beaver trade and the Rocky Mountain rendezvous. If that piques your interest, or if you find this video interesting or helpful, please consider liking and subscribing. I sure would appreciate it. In this video, I'm going to explain a technique I used to take my 2D tile map game world from 1 or 2 million tiles all the way up to a world of billions of tiles. And I did this without jeopardizing my game's performance. Stick around and I will tell you how I did this, and then I will show you in my game. Let's get started. Okay, before I show you my technique for generating billions of tiles, I wanted to take you back to a version of my game where I had a single tile map world. The world size was 512 by 512. So if we take a look at, take our calculator here and we do 512 squared. This world is made up of 262,144 tiles. Now what I want you to notice as I show you this is how long it takes from the time I click the button in the game to create the world until the world is generated. Let's do that now. So here I am in my game, and I'm going to click New. And when I click New, this is going to generate a new world, 512 by 512. This world has, and I just clicked it, and you can see how long it takes to generate. Wasn't too bad, right? Maybe 5 to 10 seconds, perhaps. And you'll notice here as I'm moving around, I'm at 0, 0. This is the upper left corner of the map, and you notice that it's seamless. I can maneuver and navigate around the map, and I just wanted to show you that the game world itself is 512 by 512. Okay, so there we go, 500 to 511, 511. So that is the size of this game world. And back when I did this, my goal was to have a wrapping world. So if you never hit the edge of the map, and the game world is, like I said, it's a pretty good size game world, 262,144 tiles. Now taking this same technique, I was able to bring the size of the game world up to 1 to 2 million tiles. But the problem that I had was that delay that you just saw when I generated a 512 by 512 exponentially balloons up until when I'm generating a world of 1 million tiles, for example, it would take 40 50 seconds before it was able to generate that game world. And that was just unacceptable to me, and I wanted to do something about it. And so I asked myself a couple of questions, particularly with the design that I'm going for. I asked myself, for example, do I need a wrapping world? Do I need a world that wraps around? And the answer is no, I don't really need a wrapping world. I could get by with a world that did not wrap around. Another question I asked myself was, do I want to stick with this concept of not using a chunking engine? And so for those of you that don't know what a chunking engine is, the design of a chunking system basically allows you to use, to create a game world. And as the player moves around the game world, and typically this is done with physics, So as the player is going from pixel to pixel, moving around the game world, new sections of the world are loaded in a chunk at a time. So if I'm heading east, the chunks from the east would start loading in as I'm making my way east. If I go west, of course, the west chunks would start loading. The idea being that the player can move around the game world, never see the edge, and the chunks, whatever the size are, would load into memory and then unload as the player moves into an area of the game world or leaves an area of the game world. Now, chunking is great, especially if you're using physics, because, like I said, you never see the edge of the world, and everything kind of loads incrementally with via the chunks that are loaded into memory. And this works. Back in several years ago when I was in Unity, I developed a chunking engine. It worked great. I had no issues with it. I really enjoyed, as a developer, writing that engine. It was really fun to work on, and I enjoyed it. It was a challenge, and I had great fun with it. But as I have begun in the last couple of years working in Godot, I started thinking, how could I maybe not re-implement my chunking engine in the Godot game engine? At that time, I had not actually ported my code over. Wouldn't have taken much to do. It was written in C# and Unity, and I work in C# with Godot. But I kind of got obsessed with this idea of how big can I make the game world, and without using a chunking system. And that kind of led me to this take on it, where the player moves, and now this isn't using physics, but the player's moving, tile-based movement, and the game world wraps, so you never see the edge, similar to chunking. But the problem is time, and that's what I alluded to earlier. It takes a long time to spin up a tile map world, of millions of tiles. So I decided recently that I would step back and kind of rethink this and reconsider how I'm implementing my game. My game is a single player 2D survival game. It doesn't have to be as big as an MMO, but at the same time, I want it big enough to give the player, hundreds of hours of playtime. So how do I do that and still maintain performance? And how do I accomplish my goal of a game world that is bigger than what I was able to get with this technique, and get it to a point where I felt happy with the implementation? And so what I decided to do was, instead of creating the game world as one big tile map, I decided to go with the concept of regions. Now, regions is a little different than chunking. Chunking, the player is moving with physics-based movement, so the player's animated, moving pixel to pixel from one tile to the next tile using the physics system, and the chunks are loading in as the player gets close to them. With a region-based solution, the player basically, region loads, the player walks around in that region and reaches the edge of the region. Stepping from one region to the next region is simply reaching the edge and stepping over to the next region. And I struggled with this when I first thought about it, because I thought, well, that's gonna hinder the concept of being in a big, massive world. But the more I realized, the more I thought on that, the more I realized that, you know what, it actually doesn't, and this might work. So I started playing around with it, and I came up with the solution that I am about to show you. All right, so I've loaded up my latest build, and I'm going to show you my new implementation that takes me from millions to billions of tiles. Now in this version, I've got a world builder. So rather than just automatically generating the 512 by 512, 262,000, whatever it was, I'm going to generate a game world that is comprised of 32 by 32 regions, not tiles, but regions. So that's 1,024 regions encompassing, in this example, a world size of 67 million tiles. Now, that already, this right here alone, has increased the size of my game world 30-fold. So let's see what this does. I have a random seed. I'll go ahead and generate. And while it's generating, you can enjoy some paintings from the 1800s. And then it brings you into the world. And this basically gives you an overview, shows you the world map, along with some native tribe placements in different regions, all a work in progress. Okay, so taking a look at it, each square is a region. Each region is 256 by 256 tiles. That is 65,536, I think it's what that is, tiles. So each region is 65,000 plus tiles, okay? And that's how we arrive at the 67 million. Now that didn't take a whole lot of time to generate, but we're ready to go. At this point, I can jump into the game. I can select the starting region. I can jump into the game. And from here, start playing the game. And I don't have to wait. And I can only imagine how long it would take to generate a world of 67 million tiles in a tile map. I'm not even sure what the maximum size of a tile map in Godot. This is Godot 4.3, so we're looking at tile map layers instead of the tile map, which is deprecated. But I can only imagine how long it would take. It would take hours to generate that. So I'm just going to pick a region. I'll just pick this guy right here, and I'll jump in. All right, so I'm in. I am in the region that I selected. Okay, so I am in region 4.3, and this fog represents the edge of the region, and I can walk around, and I can run around. The game won't be this fast, but just to give you kind of an idea, I'm showing you the performance of it. So I'm gonna come down here and I'm gonna hop to the next region. Let's see how long it takes. This is a testament to the speed of Godot, the speed of C# dictionaries, because every tile is stored in a dictionary, and the loading and saving of JSON data, encrypted JSON data, which I covered in, I think, my previous video. I talked about that. But I just want to show you this is really fast, and I'm very, very happy with it. So there we are. So I just unloaded a region, saved it to disk, loaded the next region in the world map, and brought that and loaded that in. So you can see it's very fast, it's very performant, and I can just simply run from region to region and load into each region. Now the forest regions take a little bit longer to load. I don't remember where there was a forest in my world map, and I haven't created the ability to look at the world map from here yet, but forests take a little longer to load, and that's because each individual tree has its own set of properties, and there's more properties in these trees than there would be in the grass and other features of the game. And so it takes a little longer to load, but it's not bad. Not bad at all. And I'll show you maybe when we'll take a look at a larger game world, and I'll be sure to show you how fast an all forest region loads. All right, so how did I do this? How did I accomplish this? That's what I want to show you next. All right, here we are in Paint.net, and I've thrown together this little chart or this graphic to show you essentially the theory behind what I'm doing with my regions. Okay, now I just mentioned that I have these 7 region types. Okay, now in order to achieve the massive world size that I'm going for, I create a master region. Now, the master region is generated using Perlin noise, just like I would if I was going to create a world map. All right, I would go in and I'll show you how I implemented this in my code. But if you've ever worked with Perlin noise, you know basically that when you generate your noise, and my noise is generated in a scale of 0 to 1, and so each pixel in the Perlin noise map is going to have a value, and that value is going to range from 0 to 1. And in my code, let's just, for the sake of illustration, I've decided that 0 to 0.33 is a forest, 3.4 to 6.6 is a plain, 6.7 to 1.0 is a mountain. Now at the pixel level, that would be really easy to render because I just simply create my game world, read those pixels, determine what tile type it is, and from that display the correct tile in my game world, and that's it. I'm done. And of course, again, I keep alluding to water. I'll talk about that in a second, but that's basically how it would work. So to create a game world exponentially larger, what I'm doing is I'm taking that same concept of creating a map, world map, and I'm generating it for the purpose of matching these pixel values to create certain region types. What do I mean by that? Okay, since in my game I have 3 core tile types, plain, forest, and mountain, I need, and my game world region size is 256 by 256. So with the 256 by 256, I want to create a master region where I can compare at least 3 values to determine how I'm going to generate or decide what my region type is going to be. All right, let's look at this. So here in the upper left corner, here's the first 4 pixels that I'm going to read from my Perlin noise master region. Now the master region is 4 times the size of my game world region. So each region is 256 by 256. So my master region is going to be 512 by 512. That's because I'm going to loop through my X and Y coordinates, and I'm going to pull in 4 pixels at a time, and I'm going to look at them and I'm going to compare them. I'm going to see the values and determine from this 4 what my first region is going to be. So 0.38, that's a plain. 0.31, that's forest. 0.34, 0.41, those are plains. So this combination, and I have logic that determines, do I have 1 type represented in these 4 pixels? Do I have 2 types? Do I have 3 types? And then from that, I decide what that region is going to be. So this region are these 4 pixels. From this, my code determines that this is going to be a plain region. Why? Because I have 3 plain and 1 forest. So my code says, hey, if you've got 3 plain and 1 forest, then we're going to make that an all plain region. So we have a dictionary, the region dictionary. The key is a vector2i, and I have a class, a region class that I store some region data in. And in that dictionary, I'm going to say my first region in the upper left corner up here is going to be all plain. Then I move down through my y, the next y, and my xy loops. And I look at this one and I say, okay, well, this one's plain and this one's plain, this one's mountain, and this one's mountain. Now, I have a mountain plain type. So because I have 2 and 2, I'm going to translate that into a mountain plain here. And then I move on and I make my way all the way down. I get back up here and I start over here and I say, okay, well, I have 4 forest. 4 forest is going to translate to all forest. And so this region entry in my region dictionary is going to say this region type is all forest. And then when I get down here, I have plain, forest, and 2 mountain. And my code determines that, hey, if you have 3 different types, then we're going to go ahead and make that a region type mixed, which is this guy. And so this guy, this region here, becomes mixed. The region dictionary at this position, vector 2, is going to be, so 1, 1, 0, 1, 0, 1. So 1, 1 is going to be mixed. And I continue that process all the way through the size of my game world. And so using a master region, I can look at the pixels, the Perlin noise values in these pixels, and construct or determine what each region is based on the comparison of the 4 pixels that I'm looking at from my master region. Now, once I do that, I'm essentially examining a 512 by 512 region, converting the pixels into region types that I'm going to be using in my 256 by 256 region world. Once I have that, the next thing I need to do is figure out how I'm going to handle water. Now, in my game, it was very important to me that my water stretched from region to region. You can imagine how frustrating it would be to be in a canoe in a region and you're following the river and you get to the edge of the region and you pass to the next region and you end up on dirt, on land. I didn't want that. I wanted the regions, basically the water, to span across the regions. Now, when I was showing the demo a few moments ago, you noticed the 32 by 32 loaded, and it probably took, I don't know, maybe 5 to 10 seconds to load. In truth, the vast majority of that time, I would say probably 95% of that time, was generating my water stamp. You see, the larger the Perlin noise area is that you're trying to capture, the longer it takes to generate. And so and on top of that, there's a certain limit to the size of images in Godot. I want to say it's 16384 by 16384 is the largest image size that Godot can handle. Now, in this case, my water stamp here is 2048 by 2048. In other words, my water stamp covers a region block in my world map of 8 by 8 or 64 regions. So what happens let's say the game world is, a lot bigger than what's represented here in this graphic. Well, what I do is I take my water stamp, and I call it a stamp because I'm going to be reusing this, okay? So I take my water stamp and I basically assign the water to these 64 regions. And when the player reaches this upper right corner here and moves from this region to the next region, I simply repeat the water stamp over here. Now you might think, well, if you repeat it, then the player's going to be able to notice that, and to be honest with you, that could happen, but I'm not worried about it because the player would have to traverse 8 regions to get to a duplicated water zone or a water stamp. In my mind, that's plenty. There's no reason that it has to be necessarily different from that. I could make the water stamp 16 by 16, but when I do that, I'm essentially copying or mimicking exactly what I did in my old method, where I was creating a game world of 512 by 512, and allowing and trying to calculate all the Perlin noise and assign all the tiles based on that. In other words, keeping these images small, keeping the Perlin noise generation and the image that is pulled from that Perlin noise small, keeps the time frame quick. And that's basically how I have done this. I've basically taken a region, generated a world map that's 4 times the size of the region that I'm using, then calculating a region type based on comparing 4 pixels, and just working my way down this master region, storing those type assignments into a region dictionary, and then when the player jumps into the game world, I generate a 256 by 256 region based on the region type. Now I'm going to cover this in another video, but you might be asking, well, if you have this region type called, for example, all planes, okay? If you have an all planes region type, does that mean that every region that is of plane is going to be exactly the same? No, it's not. And the reason for that is I take that player seed and I perform some math on that player seed using the XY coordinates of the region itself, and I'm able to generate a unique region based on the region's X and Y coordinate coupled with the player's seed value. And that allows every region to be different, even though those regions are of the same type. A plane region is going to be different from another plane region in the distribution of the flora, in the distribution of the river or water assets, because basically the water stamp is stretched across 8 by 8 regions. And so that's going to make this region different from this region, different from this region. And it allows also for the player to sail through region to region in a canoe and be able to navigate and work their way around the game world in that way. All right, so here we are in my code. And let me preface this by saying, if you are thinking that you're going to be able to reproduce what I've done by looking at the code that I'm going to show you, I'm going to have to apologize that you're not going to be able to do that, because I'm not going to be able to show you all the methods, all the classes, and all the code that I've used to pull all of this together. Really, the goal here is to explain the theory behind how I'm able to accomplish my goals here with the world by creating these regions, and to give you kind of the logic of how it works. And then you can take, if you understand the logic, if you understand how I'm doing this. You should be able to implement this in your own game. So this is more of an advanced tutorial in a sense. Not really a tutorial, but more of an example of how I implemented something, hoping that you'll be able to take what I'm going to show you and implement it in your game if you choose to do so. So it's not really for a beginner per se. Now, I am a C# developer by trade, and so I'm all of my code will be in C#. So on that screen where I'm generating the world, there's a call to this method, generate preview world. So once the player selects the size of the world, region size, in my example earlier it was 32 by 32, this method gets called, and it's on a background thread which basically passes back a progress, and that's how I'm updating the progress bar as we're working our way down in this code. But anyway, so I'll just give you a kind of a brief rundown of what this is doing. So we take our region section size, and we determine how big the region, the master region, is going to be. We take the world region grid size, X times 2 and Y times 2, and this is going to give us the four times the size, so that we can go through the 4 pixels to represent each region. Okay. Here's my land fast noise light for my world. Now what I'm doing here is I'm generating a mixed region on purpose. The master region is going to be a mix, right? Because I want a little bit of everything, all the region types, in my final game world. So in order to do that, I'm going to create a mixed region, or a mixed master region map. And this is how I'm doing it. And I found these values work really well in the fast noise light implementation of Perlin noise. These values work pretty well. Let me pass a nugget on to you that I learned just yesterday, I believe it was. I found out that the seed value for fast noise light in Godot 4.3, you notice that it is an integer value. Now, integers can range from -2 billion to +2 billion something or another. I can't remember exactly the number. Fast noise light will not be able to handle all of those values. And what I have found is that if the seed value gets bigger than 999,999,999, or when it reaches 1 billion, every seed value higher than 1 billion up to 2 billion, 2.1 or whatever it is, the integer max value, will produce the same noise. So be aware of that. I wasn't aware of that, and when I was tweaking my formulas that I was using for land world seed and water world seed based on the player's seed, it was producing the same noise regardless of what seed value, random seed value that I was giving it, and ended up troubleshooting and figuring out that that's what was happening. So just keep that in mind. You're limited to values under 1 billion for the seed. Okay? All right, so once I generate the Perlin noise, I grab my land image, and this land image is my region, my master region. Okay? I then save it to disk, just because it's cool to save it to disk so I can look at the raw Perlin noise. Then I instantiate a brand new copy, my game region dictionary, which is I explained in my paint.net presentation. Excuse me. Okay, so what I'm doing here is I'm looping X and Y through my region size, my region section size. This is pretty self-explanatory. I'm basically getting the Perlin values from the pixel, determining what kind of pixel that's going to be, a mountain, a forest, a plain, forest, plain, and mountain. And this pattern creates my mixed world, my master region. And then once I have that, I can then go and loop through. I'm going to do two loops. I'm going to loop through the world region grid size, so how big my game world is going to be, okay, for X and Y directions. Then I'm going to loop an X and Y, and I'm going to pull 4 pixels here. All right. X0 and X1 and Y0 and Y1. And I'm going to store them in this list. So there's 4 values that are stored in this list. And then I basically do a quick zone count. Zone count is basically I'm grouping these 4 pixels so I can get an idea of what the group is going to look like. Then I do, I basically get some zone totals here. I group order by descending so I can figure out, okay, what is the most popular of those 4? We're going to put that zone type at the top. And I get a count for the first zone, the second zone, and the third zone. Some of this is deprecated, actually, not necessary, because before when I did this, when I was working on the original concept for this, I was creating a master region map that was way larger than it needed to be. Since I'm only dealing with 3 types and a possible 7 combinations of those 3 types, I only need a region map that is 4 times, as I explained in my paint.net presentation. Okay, so if the zone count is 1, all 4 pixels are the same, then it's whatever that pixel type is. So the region type is going to be all mountains, all forest, or all plains, depending upon what those pixel values are. Otherwise, if the zone count is 2, then I do some checking and determining, okay, well, if it's 2, then if zone 1 is a mountain and zone 2 is a forest, or forest and mountain, then it's going to be a mountain forest. And these are my combinations of dual zone types, okay? Otherwise, then it's going to be mixed. So I either have all 4 pixels that are the same, or I have 2 different zones where we do not have a third type represented. And with that, I basically determine how I'm going to set the region. Otherwise, it's mixed, and that's it. So then I add that to my game region dictionary. And once I am done with that, I decide, I step down and I say, okay, now that we've taken care of the terrain, let's look at the water. So I get my water seed, I create my water, fast noise light, water, only this is going to be the 2048 by 2048. And this is going to give me my water stamp. So I save my water stamp and I'm done. And at that point, my map gen scene is going to have the data that it needs to generate the preview world that I have. And yeah, that's pretty much how I'm able to do that. I'm trying to think, is there anything else that I need to show you? This next method here is how I generate my region when the player actually gets into the game, how the region is generated, basically determining how many water stamps I need based on the world size. This is a technique that I played around with. Rather than taking the water stamp and just copying it from left to right, from top to bottom, I tried playing around with the idea of flipping vertical and horizontal. But of course, when you have a water stamp that essentially is seamless, then it's going to generate some really cool patterns that look really cool, but all it does really is make it more evident that you have copied the water region. And so I decided against doing that. Now that brings me to a thought that I want to mention here. It is very important for my game. It's very important. If I want to be able to travel the world via the waterways, then I need to make sure that my water stamp is get seamless image. I want it to be seamless. It absolutely has to be seamless. Otherwise, it won't line up when I go from region to region. Whereas up here, when I did my land, I chose not to use a seamless image. Now I could have done this. I could have said, you know what? Just like I created in my previous version a 512 by 512 wrapping world, I could create a 32 by 32 region wrapping region by basically doing a get seamless image on the land world and using that, so that if there is, for example, forest on the far right, then when the player reaches the far right and goes over, and I do provide that in my game. So if the player makes it all the way to the top of the game world and hits and steps to the next region, they will end up back down at the bottom. So the world does wrap in that sense. It does not currently wrap into the same kinds of region or the same different sections of region inside. So the tiles might be stone in the region, and you go to the next region and they turn into forest. That's okay. I'm good with that, at least for now. I may end up changing my mind later. I don't know. But I noticed that using Get Seamless Image doesn't provide as much variation in the Perlin noise, and for obvious reasons, because it has to adjust itself to be a seamless image. And that's what this little where is it? That's what this little gap here is. This is the skirt that goes around the region, or excuse me, the water image, that allows it to line itself back up so that it is a seamless image. So I use seamless for the water and not seamless, just a standard Perlin noise image for my land. And let me see, what else do I need to cover in this video? Really, I'm just getting, I'm getting, well, okay, so right here, you might wonder, how am I generating my regions? So I've got my big master region, and that master region determines the world map, kind of shows you the world map by looking at the pixels, determining the tile types. But remember, I store all of that in my dictionary. And so I get the land noise image here, and I believe actually that this piece of code here might be deprecated now. Since I have my regions loaded into a region dictionary, I can simply load the region dictionary data, and from that determine what my tile type or what my region type needs to be. And then from that, yeah, I think I'm going to end up having to deprecate that. But anyway, that's what happens when you're developing. You work on a piece of code, you write out a method, and you start developing other methods and other parts of the game, and then you go back and you look and you're like, you know what, I can refactor this, I can make it cleaner, I can make it faster, I can make it better. I guess that's why I love software so much. I love writing code and organizing, and it's fun stuff for me. But anyway, all right, so that's pretty much how I accomplished my my zone system, let me call it. And what I want to do now is I want to show you just how performant this is when we get into billions. See, I've shown you millions, but I haven't shown you billions yet, and that's what I promised to do in this video, right? show you billions. So I'm going to go back. You've seen the code. You've seen the theory of how I've done this. And now we're going to take it and we're going to expand it out. And we're going to look at 128 by 128 regions. And then there is the largest one, which I don't think I'm going to actually have in the game because I think actually it's too big for my game. But I'll show it to you anyway. So let's jump back into the game. All right, here we are. We're back in the game. And you've seen small. Let's go large. Let's go large. Generate. Okay, that didn't take much longer than small, which is very impressive in my mind, because by reusing that water stamp, I don't have to generate Perlin noise large enough to handle this size game world. And you'll notice, and since I'm talking about that water stamp, let me get rid of zone, let me get rid of terrain, let me get rid of tribes. Now let's just look at this, okay? So I'm going to zoom in. Now remember I had said that the water stamp was 8. I think that's what I ended up doing, what I ended up implementing for this. 1, 2, 3, 4, 5, 6. No, I think it's 16. 10, 11, 12, 13, 14, 15, 16, 1. Yes, it's 16. Can you see the pattern? See, you got that little bit of water there. You got that little bit of water there. There's the repeat, okay? Now, when you aren't paying attention, it doesn't look to the naked eye at first glance. It doesn't really look like it's being repeated. So I think it meets my needs. I'm happy with it. There's a trade-off between the making that water stamp larger, but then having the player wait for that additional time, and it's exponentially larger. The bigger the image, the longer, exponentially longer it takes to generate. So I'm happy with it. Here's our zones. So as you can see here, here's the terrain. So we got a lot going on. This is big, okay? Say, how big? Bound to be coding. How big is it? Well, large size is 16,384 regions, encompassing 1,073,741,824 tiles. That's what is represented here in this map. Okay, pretty fast. I originally placed individual sprites to make up each region, and then I switched over to using a tile map layer. And so what this is 16,384 tiles on a tile map layer, just like tiles on a tile map in the world, only this represents regions. And so you can see the power of this technique of using a region to create regions. That's what we're doing. All right, so I'm going to leave off with, I've got 2 things I want to show you. I want to show you Huge, which is just an experiment. Honestly, I cannot imagine going live with this. I have a pretty beefy system, so I haven't tested this on a less powerful machine, but yeah, just having fun with it. Here's 256 by 256, okay? And what that means is 256 squared is 65,536 regions, and each region has 65,536 tiles. So what you're about to look at, is 4 billion tiles. 4.2. Okay, so let's generate. And you can see, yeah, if I would have tried that in my old method, first of all, I don't think it would have worked. Second of all, it probably have taken 3 days to generate. But this is it. This is what this is what 65,000 regions look like. And by the way, this kind of gives you a visual of what a region looks like because it's the same size. So each region in the game is this size, this number of tiles. Okay? And only we are representing regions here, not tiles. So now I promised you that I would show you an all forest. So here we have here, this is all plains. This is all forest. I'm going to start here and step into here so that you can see how long it takes to go from here to here, the transition, which is the saving of all the region data to JSON binary encrypted files, and loading or generating a brand new region when we step over here. So I'm going to start. Now, mental note, look at where the water is. We've got water in the upper right corner. We've got water stretching from the upper left down to the bottom right with a dip into the southwest area of the map. Is this going to translate correctly? Is this going to match when we get into the game? Well, let's find out. Okay, so here we are. I said the water stretched from the upper left down to here. Let's open this mini map so that we can kind of see how it works. Oh. Look. There's the dip. And it extends all the way over to the far right. And then we have, if we come up here, we've got this little section in the upper northeast corner. And we can see that it is all translating correctly. And I'm going to step over here because to the right is where our forest region is. And okay, so now I'm going to step through and I'm going to show you how fast the forested regions generate. Now, that was probably, well, let's see how much that was. Let's take a gander. I've got some missing textures. That's okay. All right, so region of containing 25,480 flora generated. Okay, that took 3.2 seconds. Okay. The view refreshed with 320. That's another part of my game that I did a video on, creating my own system of blending my tiles together. That's a whole nother topic. But anyway, you can see how fast that generated, and it did. Now, when I leave this zone and go to the next zone, I have to save all this region data and then either generate the next region or load the region. Now, we know this region over here to the west has already been, I arrived there, so that region already exists. So what I'm about to show you is going from one region to the next where we are saving this region that we're in and loading the next region. Okay? And here's how fast it is. It's that fast. Now, you saw that it took 4 seconds to generate the all forest region. What I'm going to do now is I'm going to go back to that region. And let's see how fast it loads. This is not a generate. This is a load because the region has already been written out to its JSON files. So how fast is that with all forest? That fast, just like that. So if anyone tells you that JSON is slow and that don't use JSON because, you know, it's slow and it loads slow, I beg to differ. It does not load slow. Okay. JSON is blazingly fast. And that wasn't just loading one dictionary, one JSON file. That was actually loading 6 different JSON files that were encrypted, that had to be decrypted, and then placed into their tilemap layers accordingly. So, because you've got the ground and the trees and the water and the structures, the beaver dams and things like that. I mean, all that data had to load here. So very, 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 very fast. I hope that you have enjoyed my video today. If you have, would you please subscribe and give me a thumbs up? If you have any questions, comments, requests, please leave those in the comment section. And I hope that you have enjoyed this time. It has run a little long, but I hope you've gained some valuable understanding and knowledge of how you can make your game world not millions, billions of tiles in size. Until next time, I'm bound to be coding.